Hi. Today I wanted to start a new chapter. It is about modeling with ordinary differential equations. We are using these equations, their solutions, to analyze different natural processes, so to solve different problems in physics, say chemistry, economics, and other endeavors in biology, and so on. Of course, there exists almost innumerable amount of such applications. Essentially, all these science of differential equations was created for solving the applied problems. So we'll consider just a small portion of them. Now, the first thing is, the first problem is radioactivity. Radioactivity. What is this? So there exists some substance, I would say some elements, such that their atoms are not stable. They explode spontaneously by themselves. So if you take a sample of this substance, then the number of the atoms decreases. Every such explosion, every such instance of decomposition decreases the number of atoms by 1. So suppose we have this sample, and let us consider how does the number of atoms in this sample change with time. So n of t, it is the number of atoms in the sample. Now we assume for now that this number is very large, so we consider it is almost continuous variable n of t. If the number is, say, more than 100, it is already a good approximation. Now, suppose we have two times moments of time t and t plus dt. So dt is a very small interval of times. Now the basic assumption here, basic hypothesis, which is confirmed with all existing experiments, is that every atom has some probability to explode during this time, from t to t plus dt. And this probability is proportional to time interval dt with some coefficient. This means that the number of the atoms which explodes from t to t plus dt is proportional to dt with some small, with some coefficient which can be small or large. So so we can write n of t plus dt equals n of t minus some coefficient, let's denote by k, times n of t times dt. Or n of t plus dt minus n of t equals minus k n of t dt. I say that it is in fact approximate quality for it is valid for small dt. How small? No, it depends on situation, such that it should be small, but the number of these events, of these explosions of atom, should be large. Yes, during this dt. So dt should be not very small and not very large. No, okay, for now let us write this, or n of t plus dt minus n of t divided by dt equals minus k times n of t. Now, what is written here, if dt goes to 0, is nothing but derivative. So it is dn of t dt equals minus k n of t. So this is our equation. So this equation works, it describes the behavior of this function n of t if n of t is large enough, so that we can treat it as a continuous variable. For small number of atoms, say if the number of atoms is, say, about 10 or less, of course this does not work, it makes no sense, and we have to use other more complicated methods how to describe behavior. We'll look a little bit at this a few minutes later. Now let us consider, this is a well-known linear equation. It's homogeneous equation, and we can write immediately its solution. And I'm sorry. N of t equals n0 e minus kt. Here n0, it is n at the moment 0. No, the moment when we started the experiment. Yeah. No, in fact, we are solving the equation with initial condition n of 0 equals n0. Yeah. So we have this solution. N of t equal n0 e to the power minus k times t. Now, what can we do with this solution? First of all, k can be called the rate of the radioactive decay. Okay. No, this is not the most known quantity. There exist other, I would say, characteristics of the rate of radioactivity. Namely, let me write it. This is called half-life. Half-life. What's half-life? It is denoted by T with the subscript 1/2. It is a time definition. T 1/2 is defined as the time such that n at the moment t 1/2 equals 1/2 t m 0. So it is the time which is required so that during this time just half of the atoms explode. Yeah, half of the atoms explode. Now, what is the relation of half-life and the rate of radioactive decay? Sometimes this is more convenient, sometimes this is more convenient. No, okay, let us write the formula. N at the moment t 1/2 equals 1/2 and 0. N at the moment t 1/2, let me write this formula. N 0 E minus K times t 1/2 equals 1/2 and 0. Yeah, no, and 0 can be cancelled. E minus K t 1/2 equals 1/2. Let us find logarithm of the left and right hand sides. Logarithm of left hand side is what is on the top, minus k t 1/2 equals logarithm 1/2. No, logarithm 1/2 equals minus logarithm 2. Compare this and this, divide by minus k and find t 1/2 equals logarithm of 2 divided by k. No, or equivalently k equals logarithm 2 divided by t 1/2. Now numerically logarithm of 2, one moment, I'll take my calculator. Logarithm of 2 equals 0.693 divided by k equals 0.693 divided by t 1/2. So we have these formulas. No, you should not memorize this number. If you have a calculator, or you will find it anytime. No, numerically, this half time can vary in very large range. For the element uranium-238, T 1/2 is approximately 4 times 4 times 10 to the 9, 10 billions, 4 billions years. So it is close to the age of our Earth. For radium, I forgot its weight, T 1/2 is approximately 1,800 years. Yeah, so it is much smaller. We can consider for, say, artificial element fermium, 256, its atomic weight. T 1/2 is approximately 3.5 days. Yeah, for mendelevium 256, the same, T 1/2 approximately 10 minutes. But there exist elements which with much shorter half-life on one hand. On the other hand, there exist elements with much longer half-life than for uranium. Yes, there exist also stable elements which half-life is infinity, or at least we don't know, it cannot be measured. They decompose so rarely that it cannot be measured. Yeah, so we have a wide range of half-lives. Now we can consider a couple of problems, typical problems here. Which can be posed and solved for the radioactivity. So problems, example. Suppose we have a substance such that its half-life equal, say, 2 years. So in 2 years, the number of atoms of the sample will become just half of the initial. Yes, and the question: what is just a minute. Initially, mass of the sample of 0 equals m0 equals 1 milligram. No, for example, this. Yeah. So find mass at the 3. It is measured in years. So what will be mass in 3 years? No, mass is proportional to the number of atoms. Yeah. So we can write down the formula: m of t equals m0 e to the power minus kt. M0 is known as 1 milligram. What is K? We have a formula. K is logarithm 2 divided by T 1/2. K equals logarithm 2 divided by T 1/2. T1/2 is 2. If we measure time in years, logarithm 2 divided by 2 equals 0.693 divided by 2 equals, let me find it, 0.693 divided by 2, 0.346. 346. Yeah, so this is K. Now M of 3 equals E M0 E minus 3K, yeah, equals M0, it is 1. If we measure the mass in milligram, 1 times E minus 3 times 0.346 equals, let me find it, E minus 3 times 0.346 0.038 equals so we have to find e to the power minus 1.038 0.354 of what? Milligram. So in 3 years we have this. Now we can ask different question for the same element, for the same substance. Question: at which moment t m of t equal 0.2 milligram? Okay, so how to find it? We write m of t equal m0 e minus kt, and this is 0.2. K is known, k is 0.46, so m0 it is 1 times e minus 0.346 times t equal 0.2. E minus 0.346 times t equals 0.2. Now let us take logarithm. Minus 0.346 times t equals logarithm of 0.2 equals logarithm 0.2 minus 1, 6, 0, 9. Yes? So t equals minus 1, 6, 0, 9 divided minus 0, 3, 46. So divided by 0, 3, 4, 6. Just a minute. 1.609 divided by 0, 3, 4, 6, 465. 6, 0 of what? Time is measured in years, so years. So we solve this problem. Still other problem, just to show how it looks. Another example. On January 1st, say 2020, a mass of some radioactive sample was 0.1 milligram. On say January 1st, 2022, let us call it M0, equals, it is less 0.08 milligram, which is M1. What will be the mass M2 on, say, July 1st, 2026? So we ask this question. No, of course, all the numbers here are invented right here. So in this question, if you had the rate of radioactivity K, then you would find the mass at any moment by the formula which was here, and I will repeat it. So first of all, we have to find K. So we know that M of 0 equals M0. The time is measured in years. Equals 0.1 M of T1 equals M1. T1 equals, what is T1? 0 was at 2020 on January 1st. 2022, it is 2 years after that. So T0 equals 0. T1 equals 2. And here, July 1st, 2026, it is 6 years and a half. So T2 equals 6.5 years. T1 is M1 equals M0 E minus K times T1. So we have to find K. T1 is known. M0 is 0.1 milligram. E times E minus K times T1 times 2 equal 0.08, which is M1. Now let us find exponent. E minus 2K equals 0.08 divided by 0.1 equals 0.8. Minus 2K equals logarithm of 0.8 logarithm 0.8 equals minus 0.223. K equals, now we have to divide this by 2, so let me divide, so minus 0.223 divided by 2 minus 2 equals 0.1115. Yeah, okay, let's truncate it. 0.111. So we found K, and now let us find M of T2 equals M0 E minus K T2. Now we have everything equals 0.1, it is M0, E minus 0.111 times T2, it is 6.5. Equals, let us find it. So it is 0.1 times e to the power minus 0.111 times 6.5, which is equal 0.0486. It is measured in milligrams. So this is the answer. Now, in these problems we had the data of the amount of this substance, radioactive substance, at different moment, and found first K, the rate of decomposition, and then we found its amount at a given moment. Or we can start from the half-life and find K and then find this amount. So, no, that's it. Now I wanted to proceed in further. I wanted to look again at our formula. m of t, let me write down n of t, because it is the n of t, n is the number of the atoms, is the primary variable. Mass is just proportional to it. So n of t equals n0 e minus kt. So the graph of this exponent is very familiar graph of exponent. So this is t, this is n. So n equals n of t. This is the graph of this function. Now, looking at this graph, if you have, have experimental points here, how we can say, is it exponent or some other decreasing function? It's important to somehow identify exponential function. Yes. So the method for this is almost obvious. Let us plot not n of t but logarithm n of t. So t equals logarithm n of t. We can write here logarithm n of t equals logarithm n0 logarithm n0 minus logarithm of e minus kt minus minus kt. So this is a constant and this is linear, so this is a linear function. So this means that if you plot logarithm, you will see the straight line. Yeah? Straight line. The scale corresponding scale. No, practically we draw, we take here logarithm, not natural logarithm, but decimal logarithm. So it is called semi-logarithm plot. So here t, here is decimal logarithm, and correspondingly we have a grid such that we have some step, and that if you go a step higher, then the amount is growing tenfold. Yes? So during preparation to this lecture, I reproduced the simulated the radioactive decay on my computer, and really drew this plot. So I wanted to show you the result. Wait a moment. Here it is. You see here it is plotted in semi-logarithmic grid. So here is 10, 10 to the power 2, 10 to the 3, 10 to the 4. I took initially just 4 10 to the 4, 10,000 atoms, and they decay, and here we see a very exact linear function. That's it. So this I reproduced here this probabilistic model. So I took each of these 10,000 atoms and looked during a very short time dt, did it explode or not. To this I cast dice. Yes, no, use the program for random numbers. So it is really honestly, it is an honest simulation. You see that something happens here. It deviates from straight line simply because here the number of atoms is about 100, 10 to the power 2. And so here we can feel that we have discrete atoms. So there is not a continuous medium. It is medium consists of discrete atoms. So how does it look if you start from smaller number of atoms, say for 10 to the power 3 atoms? We have the following picture. Let me show you. Yes, you see this picture, and closer to the end, when the number of atoms becomes close to 10, this smooth line becomes step-wise line. Yes, because at every such step, the number of atoms decreases by 1. And the height of these steps increases because here we have not uniform grid but logarithmic grid. Here you have this distance from the time axis is proportional to decimal logarithm of n. So here I start from 1,000 atoms. And what happens if we start from smaller number of atoms, say 100 of atoms? We'll have the following picture. One moment. This picture. This picture, so you see here this stepwise character of the graph is much more clear, and at last the number reaches 1. No, in fact 10 to the 0 is 1. No, next it will go to 0, but it cannot be depicted by logarithm. Logarithm of 0 is minus infinity. So we see, but at this stage, the curve is, no, it is approximately straight. Yes, very approximately, but with larger and larger oscillations and deviations. Yeah, so why I show you all this? Let me go to the second part of my story. It is the theory of radioactive chain. it is a little bit one step farther in this theory of radioactivity. So what is the radioactive chain or radioactive family? Suppose we have a radioactive substance A. So its atoms explode and give rise to the atoms of sort B, of substance B. So A is transformed to B, and its transformation has the rate K1. So from A to B with the rate K1. So each atom of A eventually explodes, or generates some particle, like say alpha particle or electron, and remains the atom of the substance B. But suppose that the atoms of substance B are in their turn also radioactive. So with some rate they explode and give rise to the atoms of substance C. And the rate of this transformation is K2. Now, suppose for now that C is stable. C is not radioactive, yes? It's enough for now. So how to describe mathematically this situation? Let us see. A is decomposed in B, but since the amount of B and the amount of C does not affect on amount of A, so we can disregard what happens next and consider just evolution of A. So N1 of T, number of atoms of A, yes? No, N2 of T is number of atoms of B, and N3 of T, number of atoms of C. Just introduce this notation, and you have dN1 dt equals minus K1 N1 of T. The first equation. Now, what can be said about the number of atoms of B? dN2 dt. Now, here we have more complicated picture. First of all, every time appear new atoms of B because A is transformed to B. So every atom of A which explodes results in atom of B. So here one term is this same term, but with number plus, because here as many atoms of A which disappear, the same amount of same number of atoms of B just appeared. So it is K1 and 1 of T. Now, but the atoms of B also explode with rate of explosion K2, and this results in decrease the amount. So minus K2 and 2 of T. And at last, each atom of B which exploded gives rise to atom of C. So we write dN3 dt equals K2 and 2 of T. One moment, I will see how it looks. I'm sorry. I have to change. Okay, so radioactive chain, we have this scheme of radioactive decay. A goes to B with the rate K1, B goes to C with the rate K2, and 1 and 2 and 3 are the number of atoms of A, B, C as a functions of T. And we have this equation, dN1 dt is minus K1 and 1 of T, dN2 dt K1 and 1 minus K2 and 2, and dN3 dt is K2 and 2 of T. Yeah. No initial conditions for them. We have to define initial amount of A, B, and C. Let us write N1 of 0 equals N0, N2 of 0 equal 0, and 3 of 0 equals 0. No, why not? Let us take this. We start from pure N1 and see what will happen. Now what we observe, the first equation is autonomous equation. The rate of change of N1 does not depend on N2 and N3, just on N1. So we have this equation, we have this initial condition, N1 of 0 and 0. So we write N1 of T equals N0 E minus K1T. This is clear. Now what about N2? We have already found N1. Yeah, so we can write dN2 dt equals K1 N1 here and 0 E minus K1T minus K2 and 2 of T. Or let me recast it. dN2 dt plus this term K2 and 2 equals K1 and 0 E minus K1T. Now this is linear equation with right hand side, so non-homogeneous linear equation. We know how to solve them. How to solve this equation? First we find the integrating factor. Mu of T E integral K2 dt equal e to the power K2T. So this integrating factor. Now let's multiply both parts of this equation by this integrating factor. Okay, let me erase it. We'll restore when we need it. E to the power K2T dN2 dt plus K2N2 k1 n0 e to the power k2t times e to the power minus k1t. k2 minus k1t. Now we identify the left-hand side as derivative d dt e to the power k2t times n2 equals k1 and 0 e to the power k2 minus k1t. So e to the power k2t equals integral k1 and 0 e to the power k2 minus k1t dt. No, plus c. C is a constant. Which is equal, let us integrate k1 divide, so integral of exponent we have to divide by this coefficient k2 minus k1 and 0 e to the power k2 minus k1t plus c. Now we have to divide by this exponent, and you have I'm sorry, n2 of t equals k1 k2 minus k1 and 0. Here we have we divide by e to the power k2t, so remains e minus k1t plus c e minus k2t. Yes, I divide by this. Now we have to satisfy this initial condition that for 0 it is equal to 0. So n2 of 0 equals, so k1 k2 minus k1 and 0 plus c, and this should be equal to 0. So this means that C equals minus k1, k2 minus k1 and 0. And so n2 of t equals k1, k2 minus k1 and 0 e minus k1t minus e minus k2t. This is the solution for N2. Now let me a little bit analyze this solution. First of all, here we have K1 and K2, and K2 minus K1 is the denominator. We can consider three cases. Case 1, K1 more than K2. Case 2, K1 equal to K2. Case 3, K1 is less than K2. Now, first of all, we first as case number 2 is very rare. In fact, probability is 0, and I would say that no two radioactive substances have equal rate of decay. So it does not happen. So we don't consider this. These two cases happen pretty much, so we have to consider. So the first case, K1 is more than K2. K1 is more than K2. What happened here? So to have positive numbers, we have to change the order here. Instead of K2 minus K1, we write K1 minus K2 and change the order here. Why do we change? Because if K1 more than K2, then this exponent E minus K1 decreases faster than this exponent E minus K2. So this difference is also negative, and this also negative. So let us change the order here and here. N2 of T equals K1 minus K2 and 0 E minus K2T minus E minus K1T. And let us divide by E minus K2T. So let us transform it a little bit. K1 minus K2, now it is positive, and 0, E minus K2T, and here will be 1 minus E to the power K2 minus K1T. So what was the reason for this? Let's observe. Here K2 minus K1 is negative, so this exponent is decreasing. Yes? And we know from different problems and so on that exponent decreases fast. So after some time, this term will be negligible relative to this one. So we can write approximately the following thing: N2 of T approximately equal, if you neglect this term, if K1 is, say, much more than K2, which usually happens, they are very different in scale, that we just neglect it. Approximately K1 minus K2 and 0 E minus K2T. So this is in the case 1. Let me leave this for some time and go to the case 3. In the case 3, you have this formula, K1 less than K2. Then this is positive, K2 minus K1 is positive. Here this decreases, but this decreases faster because K2 more than K1. And now let us divide by E minus K3T. N2 of T, just a minute, case 3, K1 less than K2, this case. So we have N2 of T equals K1 K2 minus K1 and 0. Where is E minus K1T minus E minus K2T. E minus K1T. One moment. N2 of T equals K1 K2 minus K1 and 0 E minus K1T 1 minus E K1 minus K2T. And here again, this is a decreasing exponent, and this exponent decreases fast, and so we can write that it is approximately K1, K2 minus K1, and 0, E minus K1T. So this is neglected. So what does it mean? What does it all mean? So what means that K1 more than K2? Let me remind you, we have this chain A goes to B, goes to C. Here we have rate K1 and here rate K2. If K1 is more than K2, in the first case, K1 more than K2, K1 more than K2, then we have A goes to B fast, yes, and then B goes to C slowly. Yeah, so we can imagine that almost instantly all the substance A decomposes and becomes substance B, yes, and then substance B decomposes itself, but slow, yes, and so all the process will go as if we started from some amount of substance B, which is the same number of atoms which was in A, and then it slowly, this amount slowly exponentially decreases, yes. In the case 3, we have K1 less than K2. This means that A slowly is transformed into B, transmutated into B. There is a slow process, and then after it reaches state B, this B almost immediately becomes C. Yeah? So this means that amount of B is fed but by slow decay of A, yes, and almost immediately goes to C. So amount of B is remains all the time proportional to amount of A. But amount of A, the number of atoms of A, decreases as E minus K1T. So this means that amount of B also. So it can be said that B N2 follows N1 in this case. Yes? Or shadows N1. In the case 3, in the case 1, we have opposite situation, that B becomes almost autonomous, because almost all of atoms A very fast becomes atom of B, and then B decreases slowly, if it is in the case 1, when K1 is is more than K2. Now I also simulated this process on my computer, and let me show you how it looks. Here it is. So just look. Here is the following features. We have two substances, A and B. Initially, yes, substance A decays with the rate 3. No, in some units where time depends on how time is measured. No, say time is measured in hours or in years, and correspondingly we have rate 3. The rate of radioactivity is measured in inverse units of time, say second minus 1 or year minus 1 to the minus 1, and so on. Substance A. Substance B decays with rate 1. So we have case 1 here. Now initially we have that the number of atoms of A was 10,000, 10 to the power 4. Number of atoms of B was 0. It was here. Now if you look, if you see, yes, here the graph of n of t is in semi-logarithmic coordinates. So here, in fact, is plotted the logarithm of n. And therefore, for A, we have a more straight line, and it only becomes the step function when the number of atoms is close to 1. Here, yes, and here it is more or less perfect straight line. It is for A. For B, B started from 0, then because A decreases much faster, the rate is much larger, 3 times larger than for B. So first, almost all of A decomposes and gives rise to B. So the curve goes very steep here, reaches maximum, and then it goes along a straight line. This is a straight piece of straight line. Yes, substance number of atoms. So here the substance A almost completely decomposed into substance B. And so its number of atoms, its amount, decreases as exponent. Yes, save the last piece where we have just a few atoms of B. So this is the picture for the case 1. In case 3, what will happen if K1 equal 1 and K2 equal 3? It is case 3. Yes, it is here. Substance A. You see, it decreases again exponentially. Save the last piece where it remains less than 10 atoms of A. About B, substance B, you see it also goes more or less along the straight line, which is parallel to straight line of substance A. In fact, this means that amount of B is proportional to amount of A. Again, it is not correct in the last piece where the number of atoms of B becomes more or less less than 10. Yes, so this is what happens here. So this is a simulation which somehow confirms this theoretical analysis. Yes. Now I wanted, yes, to finish by considering one famous physical experiment. Yes, so experiment was done in 1955 by physical lab governed by Glenn Seaborg, Nobel Prize and so on. So he studied transuranium elements, which artificial elements which are heavier than uranium. They are unstable, radioactive, and very fast decaying. Among these elements was element fermium. Its T1/2 is approximately 3.5 hours. Yes, and the element Mendeleevum with the same atomic weight but different atomic number. For this T1/2, about 10 minutes. So it's very unstable. So this element, Mendeleevum, was obtained by bombardment of I forgot, Einsteinium, atoms of Einsteinium, previous transuranium element in cyclotron, It was a piece of gold foil with small amount of Einsteinium. Then it was bombarded in cyclotron. Then it was dissolved in the acid, and then the chemically separated Einsteinium and Mendelevium, which was obtained there. So it was a race against the time because of this short time. So what they saw, yes, the scheme of the chain, radioactive chain, was the following. So Mendelevium was decaying into fermium, yes, with some, say, K1. K1 corresponds to this half time. And fermium was decaying. In fact, the atoms of fermium were divided in two or more fragments, smaller atoms of about half the mass. So it is C. C is a mixture of different atoms of smaller masses, which we don't consider now. Because this process with rate K2 does not depend on what happens here. So let us find what is K1. T1 and T1 half 2. Logarithm 2 divided by T1 half 1. Let us measure time in say hours. It is 0.693 divided by 10 minutes 16 16 equals 0.693 times 6 416 158. Yes, K K2 equals logarithm 2 divided by T 1 half 2 equals 0.693 divided by 3.5. 0.693 divided by 3.5, 0.198 also. So we see that K1 is much more than K2. Yes, this means that we have the first situation. So almost all Mendelevium first very fast decays into fermium, and then fermium decomposes. Yes. No, we can write that N1, it is amount of Mendelevium, equals N0 E minus K1T, and find how it decomposes. So if T is about 1/6, yes, then it is no, okay, so after half an hour it will practically completely disappear. Yes, and N2 is approximately equal N0 E minus K2T. So first it decomposed, mendelevium decomposed into fermium, and then fermium decreases exponentially by itself. Yes, so we have the first picture here. So let me remind you this picture. Yes, one moment. So if this is amount of mendelevium, this amount of fermium. Yeah. Now let me show you the actual picture, actual result of the experiment. Here it is. Here is one experiment. They took initially 47, they had 47 atoms of fermium. And you see this curve, it is the number of atoms of fermium as function of time. Now this experiment went for 1,200 minutes. It is 20 hours. No, simply because the half-life of fermium is 3.5 hours. Yes, so during this time 20 hours all the atoms of fermium exploded. Yeah, so it was enough time for them. It is for fermium. Now, when they took mendelevium, after all, it turned out that had only 7 atoms of mendelevium. Yes, and this is the staircase which shows how the atoms of mendelevium, one after one, first they all very fast transformed into fermium, and here we see how these atoms of fermium exploded, and this line which somehow describes this staircase is parallel to this line. What does it mean? It means that it has the same half-life. So this is one of the most famous graphs in the whole nuclear physics. Okay, so let us finish with the radioactive decay, and then we will consider different models. For now, have a good time. Bye.